Section 2.9, Bases and Dimensions in Lay's textbook, which happens to be section 4.4 in Edward's textbook. What's a basis of a vector space? A set of vectors v1 through vk in a vector space, provided the vector space is a finite dimensional, that means it has finite number of objects in it, is called a basis for the vector space V, provided two conditions are satisfied. The set of vectors v1 through vk are linearly independent and they span the vector space. Remember, spanning set is finding the building blocks for a vector space, and linearly independent guarantees that those building blocks are the minimum number of vectors you can choose to build any other vector in that space. The number of vectors in any basis is the dimension of that vector space. So the dimension of the vector space denoted by dim of brackets v, which stands for vector space, correct, is the number of vectors in a basis. Special case, if the vector space consists of zero vector only, so the dimension is zero. Keep in mind the what? Vector space with what? Zero and single vector are called improper subspaces. In other words, the zero vector and vector itself are called subspace of what? Of the given vector space. So the question arises that let's say you have a differential equation y double prime plus y is equal to 0 on I is an open interval, okay, interval. The question is determine a basis for the solution space. So solution space is a space which consists of all solutions of the second order homogeneous differential equation, linear of course. You and I, we both know from previous chapters, the solutions are sine and cosine. So, because sine and cosine are linearly independent, because if you take the ratio, it doesn't come up as a constant. Also, if we can, if there, for any C1 and C2 as has been any real number, I can form this combination, linear combination, and lo and behold, that also satisfies the equation. In other words, any solution of this differential equation can be written as linear combination of sine and cosine. Therefore, sine and cosine span the solution space, and they are linearly independent, so we have minimum number of vectors in a basis. Therefore, the conclusion is the set of vector functions, in this case sine and cosine, form a basis, and the dimension of the solution space is 2. So that's the reason we have the general solution as linear combination of two functions, because it takes exactly two linearly independent spanning set of functions to create any other solution in the solution space for this particular vector space. So that's why we have the fundamental solution consists of two, therefore that results in two constants, namely C1 and C2. The dimension for some commonly used vector spaces, the dimension of Rn is n, so that in particular, the dimension of, let's say, a three-dimensional space happens to be 3, right? That's obvious, you're in three-dimensional space, which means it takes minimum of 3 linearly independent vectors, which they happen to also span the vector space, determines the dimension or dimension of the vector space. The dimension of m by n, that's like m as in Mary, n as in Nancy, is m times n. The dimension of a square matrices is n squared. The dimension of a polynomial of degree n or less is n plus 1. One of the question is the following, which is determine if these two vectors in R2 form a basis for R2. For linear independency, you can either say, well, the vectors are not parallel, they are not collinear, therefore they're linearly independent, or you can augment these vectors. Remember the columns of this augmented matrix is each of these vectors. So V1 is this guy, V2 is that guy, augmented with 0, 0, based on definition of linear independency. And make sure at the end of the day, what you have come up with the conclusion they are linearly independent, because row echelon form has no what? Row of 0. Okay. For spanning, let what? X, Y be a random vector in R2. Form the linear combination and set it equal to X, Y. Notice for linear independency, we set the linear combination equal to 0. For spanning, we set it equal to a to a what? A random vector in whatever the vector space you are in. In this case, if you put this in row echelon form, notice at the end of the day, you have what? Leading one in each column. So that means the system is consistent. Therefore, what? You have a solution, therefore they span. So the conclusion is, yes, they do form a what? Basis for R2. And because you had 1 and 2 vectors in the basis, therefore what? The dimension of R2 is 2. And that makes sense. Yes, you are in 2 dimension. So it takes minimum of 2 vectors to what? Form a basis, provided the vectors are linearly independent and they span. So one of the nice facts about this section is as follows. Suppose the dimension of the vector space is n, and you have n many vectors in what? In S, the set S. And suppose set S is what? It consists of n many vectors, and the dimension of the vector space is also n. So S is a basis for what? V. So these are the consequence of this scenario. S is linearly independent, so the number of vectors in the S is what? Linearly independent, and the vectors in S span what? The vector space V. The morale of the story is as follows. If the number of vectors in a given set matches the dimension of your vector space, in other words, this guy is a subspace of this, but the dimension of the subspace matches the dimension of the vector space, all we have to do is what? Is either what? Verify the condition of linear independency or spanning, not both. Before I show you what I mean by that, let me tell you what the geometric description of this subspace of R3 is. R3 can have what? 1, 2, 3, 4 subspaces. If the dimension of the subspace for R3 is 0, then that means what? The geometric interpretation is just 0 in R3. If the dimension of the subspace is 1, then geometric interpretation is what? You have a line through the origin in R3. If the dimension is 2, then it's a plane, what? Through the origin in R3. So this would be the origin. If it is 3, the dimension of the subspace matches the dimension of the vector space, then subspace is the vector space itself. However, warning, if S is a subspace of vector space V, and the dimension of the vector space is n, dimension of the subspace is less than n, unless S is the same as the what? Vector space itself. In other words, the dimension of the subspace of a vector space cannot exceed n. It could be equal if it is the same as the vector space, but it cannot be more. But it's always less than n, and occasionally it's equal to n. Do you see it? So let's do a little problem here. Suppose this is a set S, subspace of what, R3. Question is, does S form a basis for what, R3 or not? Well, keep in mind the number of vectors in your subspace is 3, which matches the dimension of the vector space itself, which is R3. So that just means, by that fun fact which we just went over, either you prove they span R3 or they're linearly independent. Whichever you feel comfortable, go with that. I went with linearly independency. So what I did, I took the linear combination of these guys, set it equal to 0. I came up with this homogeneous system of linear equation. And then uh, either you can put what, this augmented matrix, which is this guy right here, 1 2 1 3 negative 1 2 1 1 negative 1 0 0 0 in row echelon form, and see for yourself. You are not going to end up with any row of 0, so that determines the linearly independent. Or if we know what determinant is, because you got 3 equations and 3 unknowns, you can always find the determinant of A, which is the coefficient, the matrix of what consists of vectors v1, v2, v3, and see if the determinant is not equal to 0, therefore they're linearly independent. So, because the number of vectors matches the dimension, either I have to verify spanning or linearly independency to prove that these guys form a basis or not. So in this case, I chose linear independency, and I found out they are linearly independent. Therefore, these vectors form a basis, and the dimension of the what? R3 is 3, which is the same as dimension of the subspace. However, here's a counterexample. Suppose now you got 3 vectors, but they happen to be in R4. In other words, your vector space is R4, but the subspace consists of these 3 vectors in R4. Dimension of R4, we just learned it's 4, but you only have 3 vectors, and we need 4 linearly independent what? Vectors in order to span. So we don't have enough vectors. So therefore, these vectors cannot possibly form a basis. Remember, you have to have at least this many. Dimension of a vector space determines the minimum number of what? Vectors it takes to build everything else in that space. And to do that, we have to verify that they are linearly independent and they span. But now you have only what? 3 vectors in R4, so you don't have enough vectors to build everything else in that space. Therefore, they do not form a basis. What would be a basis for this particular second degree polynomial, 2 plus x minus 3x squared? Well, if we rewrite this as 2 times 1 plus 1 times x minus 3 times x squared, looks like these guys will span any P2, any polynomial of second degree or less, and they are linearly independent. So therefore, the conclusion is, okay, they form a basis, these guys, these 3 functions, they form a basis for P2, all set of polynomials of degree 2 or less. And because you have what? 3 functions in your basis, therefore the dimension of P2 is 3. Remember, the dimension of Pn was always n minus 1. So the dimension is always 1 more than the degree of the polynomial. So keep that in mind. And now let's do 2 not usual, your standard type of problems, and see How would you find a basis for a set of vectors of the form A, B, C, D? Obviously, you're in R4, yes? For which A is equal to B plus C plus D. So we are talking about not R4, that's our vector space, but this is our subspace, okay? In other words, we are looking at what? A subspace which contains what? This kind of vectors. Subspace of R4 contains this kind of vectors, but it's not just any vector in R4. It's the one which the first element is the sum of the remaining elements, B, C, D. A, B, C, D happens to be a bunch of real numbers. So A, B, C, D are real numbers. So what happens is, if I choose any specific what? Uh, what? A vector in subspace of what? Vector space R4. This is how they look like. Notice what I did. I replaced the what? A with B plus C plus D. So if you factor out the B, you get this. If you factor out the C from all these components, you get this. Factor out the D, you get that. So therefore, a basis for a subspace, not R4, but a subspace of R4, happens to be consist of these three vectors. Why? Because I was able to write it as linear combination, and so that means they span, and they are linearly independent. You can verify that. So therefore, there are three vectors which can be used to generate any other vector in the subspace of R4, which has this format. But because I got three vectors in my basis, therefore the dimension of the subspace is 3. Remember, the dimension of a subspace is always less than what? The dimension of the vector space. In this case, remember the vector space was R4, but the subspace consists of all those vectors in R4, which they satisfy this equation. So I didn't expect the dimension of the subspace to be greater than my what? The dimension of the vector space, unless subspace is the vector space itself. The next question is find the basis for solution space of this system of homogeneous equation. Notice you got two equations, but three unknowns. So put this in augmented form. There it is. Okay, put it in row echelon form. There it is. Notice x1 and x2 has leading 1, x3 doesn't. So x3 is a free variable, so we're going to let that be t. And then I'm going to express x1 and x2 in terms of t. So lo and behold, the solution for that system of equation, you have infinite many of them. It's in the form of 11t, 7t, and t. However, if you factor out the t, this is the only linearly independent vector in the solution space, because everything else is just a multiple of this. So therefore, a basis for solution space is not this, it's just this single vector whose components are 11 and 7 and 1, because every other solution to this system of homogeneous equations can be built or generated by this particular what? Vector. So this guy forms a basis for a solution space of equation system 1. And because there is only one what? Vector in our basis, so that's dimension of the solution space for this system is 1, not infinite, it's 1. Thank you.